And this is my today's outline. And at first, I will talk about introduction and the experiment and the results and discussion. And finally, I will give you some conclusions. First is introduction. In recent years, the study of semiconductors device stability in extreme environments has garnered widespread attention. And here's the photodetectors play a vital role and are required to operate in extreme environments, and including about low temperatures, intense ultraviolet radiation, and extreme humidity, and corrosive atmospheres, and hazardous gases, and intense mechanical stress. In the future development of technology, photodetectors play a vital role, and within decades, several studies has been conducted on light-emitting diodes, as known as LEDs, degradation in solid water vapor ambient. These studies confirm that the solid vapors are capable of damage and age the LEDs devices. However, the degradation of zinc oxide-based sensors caused by solid water vapor ambient has not been clearly reported yet. So we study the solid vapor, how to influence our zinc oxide-based photodetectors. And here's the experiment. To grow zinc oxide nanorods on silicon dioxide and silicon substrates, 0.66 grams of zinc acetate and 60 moles of ethanol and 2 drops of MEN in a mixture form the C-layer solutions. And then the C-layer was spin coated on the substrate, and then the coating substance was put on the heating plate. And the zinc oxide nanorods were grown by the hydrothermal methods and with zinc nitrate. And to spread the salt water mix on the sample, the solid vapor was generated using a humidifier, and this emulation aims to replicate the condition of the sensing device with a high salinity environment. And here's our results and discussion. And the figure 1 is an illustration of setup for the photodetector degraded by the solid vapor. And figure 1A shows the setup of the photodetector degraded by solid vapor. Photos and optical microscope, OM image of a fresh device and the device subject to saline degradation are shown in figure 1B and figure 1C. This is figure 1C. Figure 1C OM image in the photodetector before and after solid vapor. And to zoom in the damage in the OM image, the OM image revealed that the defilement caused the vapor can be observed both in the electrode areas and zinc oxide nanorods areas. And figure 2A is the SEM image of a photodetector after solid water with a lower magnification rate. And SEM image of a photodetector picture B is before, and the figure C is after solid water with a higher magnification rate. In figure 2A and B and C, for large scale of the observation, SEM image with a lower magnification, you can see in the picture A, which may be caused by the solid water vapor, can cause the picture C after solid water with a higher magnification rate. And figure 2, D is a TEM, and picture E is an HRTM image. And picture F is the black part is the crystallization of zinc oxide, and the light part is the remaining material after the destruction. And here's figure 3. The figure 3 is the full XPS spectrum of the device after solid vapor. Picture B is a CO2D TLPS spectrum of the devices after solid vapor. And figure 3C is an excited pattern of the device after solid vapor. And the picture D is a Raman spectrum. Figure 3C also show the emergence of the nitrogen and sodium hydrogen crystalline phase suggestive of the anexial attachment of zinc oxide nanorods. And the following is a convocal images of the fresh device and the device subjected to solid vapor for 3 minutes and 9 minutes. And figure 4 is the IV curves. To study the electrical properties influenced by the solid water vapor, the current voltage IV curves of the fresh device and the treated device were measured as shown in figure 4A and B. The results reveal that the ohmic contact behaviors were changed by the incorporation of the solid water vapor. And figure 5 is the UV photon response for the device subjected to solid vapor for 0 minutes, 3 minutes, 9 minutes, and 15 minutes. And the picture B is the device subjected to the solid vapor for 3 minutes, 9 minutes, and 15 minutes. We can show clearly the 15 minutes line in the picture B. And this is the UV response. The picture C is a device subjected to solid water vapor for 9 minutes and 15 minutes. And the picture D is the UVB spectra for the fresh device and the device subjected to solid vapor for 9 minutes. And here's the conclusion. We can see the photosensing degradation of zinc oxide nanorods-based photodetectors could be observed while the device was undergoing solid water vapor. And the material characterizations revealed that the NaCl did attach the nanorods owing to the presence of NaCl on the anodes, but the residue did not cause the stress on the nanorod surface. According to the reliability test and the material analysis, solid vapor can damage the zinc oxide nanorods, and both in a large scale and a small scale. And hence, the sodium ion protective layer may be required for the future area photo detection applications. And that's all my presentation. Thank you for listening.
Thanks, the speaker, for being very much on time. Any questions from the audience? All right, maybe I got one. So, can you go back to your TIA image? Yes. So, how would you say it's been degraded? There have been some degradation after being exposed to salt vapor. How do you quantify it from these NCT images? If I was just looking at it, if you look at the dark image, how do you think? Why do you think it's being damaged?
Because
perhaps there's some more dislocations there, or some formation of oxidation, stuff like that.
we didn't talk about this.
Okay, cool.
So I'm sorry to.
That's all right. But yeah.
Sorry.
So fine. It's fine. Any others?
I just wonder, that's the surface of
Yes. This one.
you got differential patterns? Like SLED or to check the phase.
We haven't used this in a few hours.
Yeah. Okay. Yeah. Usually, that's probably a really good technique to determine the crystal crystallinity of your material. All right. Let's thank the speaker again.